Yes, sir. Okay, we are going to start. We are waiting for 2 to 3 minutes more.
Okay, no problem. Sure, carry on.
Participants, 30 participants have already joined. We are waiting for just to join 2 to 3 more. Then we'll
Okay,
start.
no problem, no problem. Carry on.
Mhm. 35 participants have already joined. So let us start now, I think. Somadev? Somadev?
Yes, sir. Okay.
Uh,
So, good morning,
I think,
everyone.
yes.
We are here for the webinar titled as Engineering of Smart Materials, Laboratory to Technology. Uh, Before going into the details of this particular program, let us first thank our speakers, Dr. Manas Panda from Jadavpur University and Dr. Nimai Mishra from SRM University in Andhra Pradesh. Today, we shall be talking about the materials that are actually modified to respond in a controllable and reversible way, modified some of their properties as a result of the external stimuli. Okay. Now, for each and every material, the laboratory experiments are very, very important. We need to understand the properties at first. Then we will need to modify their properties in such a way that it will be of our use. Okay. Now, say for example, synthetic spider web. It is actually very stronger, even stronger than the steel. It has great elasticity. It has the applications in the field of bulletproof jackets, waterproof adhesives, etc. So obviously our speakers will be telling us more about it. But before going into that, first we would like to hear from our Honorable Director, Dr. Piyush Palroy. Sir, please say a few words for encouragement and for the students and to our speakers.
Hello, Shomodeep.
Yes, sir.
Have you finished your?
Yes, sir. I finished. Please tell us a few words.
Okay, okay. At the outset, I want to extend my Happy New Year 2021 to all the participants. Let this year bring happiness, peace, and joy in everybody's life. On behalf of Dr. B.C. Rai Engineering College, Durgapur, I heartily welcome you in this important one-day national level webinar on emerging of smart materials laboratory to industry coordinated by the R&D cell of this college. As you all know, that smart materials refer to those materials which have the ability to change their composition or structure, their electrical and or mechanical properties, or even their functions in response to some environmental stimuli like temperature, pressure, magnetic, electric fields, chemical or nuclear radiation. The field of smart materials and structures is evolving from high-end, one-of-a-kind products for medical, military, aerospace applications to the point of viability for mainstream, high-volume, low-cost products for automotive applications with significant benefits including high energy, power density, reduction in vehicle mass, added functionality and design flexibility, and decrease in component size as well as cost. So you can understand the importance of smart materials. The world of materials is an exciting and challenging field of research since it has always played a dominant role in evolution of human civilization. The demands from aerospace, defense, automotive, and industrial branches on more advanced and innovative materials has led to the development of a new generation of materials with much better performance and capabilities than the existing conventional structural and functional materials. As a result, the era of smart materials has started. This is the beginning of smart materials. Distinguishes smart and nanomaterials. Smart materials perform both sensing and actuating operations, whereas many nanomaterials are capable of self-assembly. So at this juncture, we should say that it is therefore very pertinent to conduct this important webinar, wherein we have two very eminent speakers, namely Dr. Manoj Panda, who is the Assistant Professor of Department of Chemistry, Jadavpur University, and Dr. Nimai Mishra, Assistant Professor, Department of Chemistry, SRM University, Andhra Pradesh. I thank Professor Chandan Kumar Ghosh, Head R&D, Sri Shomodeep Das, Assistant Professor, Civil Engineering Department, for coordinating this webinar along with all other colleagues of the R&D department. And I wish that this webinar will be a very thought-provoking and inspiring one. I wish the event a great success, and I welcome you all in this very important webinar. Thank you very much and wish you all the best. Over to Shomodeep.
Thank you, sir. Thank you for your words. Now, we will start with the proceedings. First, we have our speaker as Dr. Manoj Panda. He has completed his PhD in the year 2010 from IIT Bombay, and after that, he has been associated with different universities like NIIST Trivandrum from 2016 to 19 before joining the Jadavpur University. He has accomplished a very good career academically, and obviously he was awarded as the Emerging Investigators in Crystal Growth and Design, that is American Chemical Society in India 2019. He is also the member of Chemical Research Society of India, Material Research Society of India, Indian Crystallographic Association. His interests are in the inorganic chemistry and solid state and the material chemistry. So, if I go on telling more about his achievements, it will take a longer period of time, which is not of our interest for this particular purpose, but we would like to eagerly hear from him about the topic he has studied, and also he has done the research on this particular topic. So over to you, Professor Panda.
Thank you, Shomodeep, for your kind introduction. Let me start my presentation first. And so at the onset, I would like to thank organizers, specifically Director Professor Piyush Pal Roy and other members of the committee, and Dr. Shomodeep and all the members of the organizing committee. Very good morning, Happy New Year, and to all the students also. So it's very warm good morning to all of you. So it's really a pleasure to present a popular talk, which is not a research talk actually. It's a talk which is concentrated on popularization of the science on the smart materials. And I hope all the students will enjoy my talk, because since this is an engineering institute, I have focused my talk more on the application of the smart material. Obviously, without fundamental study, you cannot go for application. But still, too much fundamental may discourage. I mean, may lose their interest. So, I more or less focused my talk on the application side of those smart material. Okay, so let me start slowly. Is my presentation visible to all?
Yes, sir.
Yes, sir, it is visible.
Okay, let me figure out one more thing. Okay, so you can see my cursor, right?
Yes, sir.
Okay, so let us talk may start, and the title of my talk is Bio-inspired smart material, fundamentals and application. So when you say about bio-inspired smart material, that says something about the nature, right? And we all are owed to nature, because nature is a wonderland of technology. The natural entities or natural, natural organism, the technology which is developed by natural organism is a evolution of thousand years, and that is not really possible to achieve by working in your lifespan in the laboratory. But still we are trying to do, and we are trying to manipulate the material and their fundamental properties, so that we can achieve something which is close to the nature. But it's really a difficult task. It is not important how the mechanism. It's not important to follow or copy the mechanism from the nature, but at least we can learn from nature, the phenomena. Whatever the phenomena the natural entity is exhibiting, we can follow the same phenomena or copy the same phenomena and develop the material in the laboratory with the same similar phenomena. In that case, we will at least develop some material which are bio-inspired material. But before going to the bio-inspired material, let me tell you about what are the smart material, what is called smart material or stimuli responsive materials. These smart materials are actually stimuli responsive material. That means they can absorb or sense different kind of environmental stimuli. These are light, either sunlight or UV light, or even man-made light, or the thermal heat, the abundant heat from the sunlight, or even many process has many abundant heat. So if we can utilize heat and utilize them for developing a smart material or sensing different volatiles using a smart material, then at least our goal will be successful. Okay, there are other stimuli also. There are sound or pressure, mechanical pressure, or even humidity of the atmosphere. There are certain materials that can show different kinds of actuation based on the humidity gradient in the atmosphere. And the best example is the plant. In certain environment, the plant do not grow. Their roots do not grow. Their leaves do not grow. But at certain environment, their roots started flourishing, mainly in the rainy seasons or something like that. And in winter season, you can see how they behave. Everything is dried up or something like that. So those are the lessons we can learn from the nature and utilize them for developing our material in the laboratory. So when I talk about smart material, it has two different stages. So smart material actually do sense in the first stage. So they have a capability of sensing all these external stimuli, and those sensing and response. The second stage is response. The response in a useful way, so that we can utilize them for our technological purpose or very useful for our daily purpose. Okay, and there is a energy conversion or energy transduction within the material. So that is very important. So this ability, energy conversion and energy transduction within the material, is a very important property that was observed only few number of materials among several materials. So that is why smart materials are very important, because they have the unique capability of sensing the energy from the environment and then transforming the energy into different energy in a useful way. so that we can utilize this. So that is why smart materials, smart systems are very important for developing, robotic machinery, or even different types of sensors and many other applications I'll be talking about. So what I have we'll be talking about. First, I will show you some examples of different types of smart material, and then I'll go for the bio-inspired smart material. Means the smart material, smart technology, which are really directly inspired from the nature. In fact, most of them are inspired by the natural phenomena. Phenomena we are inspired by nature, but I'll try to correlate how they are, very important to mention the natural phenomena with the developed material, which is developed in laboratory. So here are the points of few points of smart materials. Smart materials change their properties in response to heat, light, or something else. I mean, either any other stimuli. It can be moisture, it can be pressure, and change their properties means either physical properties or chemical properties or mechanical properties, whatever it is. So physical properties means they can change their volume, they can change their shape, they can change their density, whatever it is, or they can change their volume. External shape, etc., etc. They can change their chemical properties also. So based on those property change, we have to think of their application in different or respective areas. Okay, and there are certain material which we can change back to their original state when the heat or light is taken, which is taken away. I mean, there's a reversibility is there also. So if you apply one stimuli, they change their shape, and then if you remove the stimuli or apply different stimuli to bring them back into the initial state. So these are the reversibility of their nature, which you can something is very important for certain material. Okay. And in everyday life, we are encountering smart materials, from photochromic glasses like sunglasses. You know that in the dark it's very transparent, and if you go out the sun, it becomes black. So these are photochromic materials. So it's responsive to photo. I'll talk about each of these in details in the next subsequent slide. There are thermochromic materials also, which can change color in response to temperature. Photonic crystals, these can change color depending on the angle you are viewing. Hydrogel materials, touch screen material, liquid crystal touch screen material, or even the gas lighter, the cigarette lighter, or the oven lighter. You can see these are the piezoelectric elements. So if you just put a frictional force, they will spark the electricity. And that electricity actually, during that process, that electrical spark actually fuel the gas which is coming out from the gas chamber over here. So this is how this gas lighter actually works. Now, from the very beginning of your birth, since the day you have see the you see the light of this world, you are encountering the smart material, and your mom has probably used this kind of things so that you do not spread the nuisance here and there. And this is nothing but a smart material which can change their shape in response to water molecules. So this is hydrogel material. Hydrogel means these are materials which can form gels, highly viscous solid, semi-solid kind of thing when the water is absorbed in it. And this material is nothing but a sodium salt or polyacrylic acid. It's a long chain carboxylic acid, and when it is made salt, so it becomes salt means it's an anionic part, and this cationic part is sodium ion. And it is a super absorbent polymer. That means it can absorb more than 1,000 times of its actual mass. Okay, so it can absorb water which is 1,000 times more than its actual mass. So this has a tremendous amount of water absorbing capability. And the main important thing is that after absorbing water is no longer fluid inside. So it is trapped inside surface. And that is the chemistry behind this baby diapers. So the day long time they can pee on that, and still it is not wet, because they can take 1,000 times more water than its actual boil. And the mechanism is already explained here. The negative charges, when they are negative charge, means when they are salt, because of the repulsion, they try to expand as much as possible. That is why you see they, after absorbing water, they are expanded. They are expanding in their volume. And as soon as they expand, their viscosity also increases, so that the water molecule inside that cannot behave as a fluid, so they cannot flow. So that is why they are trapped and they are not wet. So that's the chemistry of one of the smart material, which is hydrogel. Second smart material I'll be talking about, which is thermochromic material. And thermochromic, it says that it's a thermochromic. Chromism means color change. Thermo means thermal is the stimuli. So color change as a result of thermal stimuli. Now this is again, it can be reversible or it can be irreversible. You can see it, and here are just one example I am showing. There are plenty of examples. If you go to the literature, you can see there are plenty of examples of thermochromic materials. So this material, it is a polydiacetylene film, and which can undergo thermochromism. As you can see, at particular temperature, at 20 degree temperature, its absorbance profile is something, and at 90 degree temperature, the absorbance profile is different. So based on this property, you can see they is changing their color. And here is a demonstration. You can see at 20 degree it has a blue color, at 110 degree it has a pink color, and you can see from this video also how the color is changing. So 110 degree means water should boil. That's a reference temperature point, and here is the initial color of that at 20 degree, and then slowly it changes to pink. You can observe from here, and then again it cool back. It can come back to the original violet color. Okay, so these types of materials are very important for different applications. I'll go to the application in the next subsequent slides. So when it's cooling, you can see how slowly it is coming back to the original color. And the mechanism of that color change is nothing but a supramolecular interactions inside the this polymer film. So there are several types of hydrogen bonding: intramolecular, intermolecular hydrogen bonding, and they are rearranging themselves within the thin film, so that their absorption property is also changing. So the details can be found from this paper, but I don't have time to discuss all the details here because of the time restriction. And there are many papers. If you just type a thermochromic material in the Google, and you will find plenty of papers. And many of these videos and pictures have been taken from website just for the presentation purpose. None of these are my research work, but since this is a popular talk, it's not a research talk. I have tried to make the talk more interesting to you, and that is why the more demonstration will be coming up in the subsequent slide. So here are more example of thermochromic molecules. You can see over here. You can see these molecules which changes their configuration. You can see some kind of cyclization is happening over here, because of which it is changing their color upon heating. Okay, and it can be reversible upon cooling also. Bisphenol is a very common, and it's commercially available also. Bisphenol compound is also a important thermochromic pigment, which is red in the initial stage, but once you start heating, it becomes white. So that is why these are also very useful for commercial product. And here is electric kettle, which is you can see when hot water is poured on it turns red, and when the cool water when it get cool, then it is blue color. Okay, let me show you some application videos. So based on these properties, scientists has developed different types of material, which is thermochromic cup, in which you can really see the color from the outside without even sipping it, and you can see whether tea or water inside it is hot or cold. Okay, as you can see, this cup has a pigment over here. It's a black pigment. So when it is hot, it becomes transparent or white. Okay, so let's see the video first. So you are pouring hot water on it, and slowly this thermochromic pigment is getting heated and changing its color. You can see over here the color is changing here, and also changing over here, and you can see the some writing is hidden in that because of that. Okay, and then you can again cool it. It becomes cool with water. It becomes black. Okay, as soon as the hot water is inside, so it will again turn to white. But once you pour the water from the inside, then it will again return to its original black color. This is something which is ladies will really be interested who are present in this audience. I think they can also this kind of nail polish is currently available, but might be very costly. I'm not sure whether in India it's available or not. So they are made of thermochromic material. When you dip your nail in the hot water, it can reversibly or irreversibly change the color. So that depends on the pigment. If it is reversible, once you take out from the hot water, it can come back to the original state. Or if it is irreversible, it will remain to the same color even after taking out from the hot water. Okay, so these are few applications. There are many other applications of thermochromic materials which has been developed, but I give you just few examples in order to make your mind more towards engineering application. Another interesting compound is or material is photochromic material. So the title itself says that it changes color with photoirradiation or light illumination. So that can also be reversible or irreversible. Now, this was a long story. This is really a long story. From 1952 or even before that, there are molecules which used to show different types of photochromic, but this was not developed too much because the mechanism was a little unclear very for a long period of time. But slowly it developed, and now these photochromic materials are really very interesting and have many applications. So one of these type of photochromic molecule is Spiropyran. So this is the basic structure of Spiropyran. You can see this part is responsible for your photochromic change. So when it is in a closed state, it is colorless form. It's colorless, but when it is open, it becomes more conjugated. So here it is not conjugated. When it's become open, it more conjugated. So this actually open if you irradiate with UV light. So UV light induced ring opening of the spiropyran and then to merocyanine. So the ring open form is called merocyanine, and that is why it becomes more colored form because it's conjugated. So it decreases the homolumo gap and become more colored. And based on this, there are many parameters that needs to be decided or needs to be checked before it's go for the application of whether it is application for different material like photochromic glasses or photochromic windows and all those things, because the color stability is also important. After changing color, how long it does stay in that form. So the lifetime of this ring opening form is also very important. Those who have very poor lifetime, they cannot be used for specific applications. So that depends on application and the property it is showing. So there are many substitution you can change over here, you can change over here and get the different types of lifetime and other property changes. Okay. Here are some videos I can show you. These are another interesting molecule, which is diarylethene, which is one of the best molecule which shows photochromism as a result of ring opening and ring closing. So initial form is ring open form, and as you irradiate light, 365 nanometer light or any other 405 nanometer light, low wavelength light, it undergo ring closing. Ring closed form. So this is ring closed form, and this ring closed form is deeply colored because of the enhanced conjugation of that. And then again, if you irradiate light with different wavelength like visible light or even just simply heat it, it come back to the original state, so colorless state. Okay, so let me see some videos over here. Here are some pictures you can see. These are the crystal before irradiation, and these are the crystals before after irradiation. Obviously, each crystals are different substituents, not the same crystals. So these are the substituents by which you can change and you can get the different colors. So really very nice set of or nice range of colors you can obtain from this kind of crystal. So let us see a hands-on video. In fact, this was recorded by me during my I'm sorry for the sound of the video. I should have removed the sound, but at this moment it's not possible. Some of my colleagues in the laboratory was talking, so the sound is coming. Can you hear me?
Yes, sir, we can hear you.
Sorry, I muted the sound again. Okay, so you can see here this one also you can see after irradiation you can see how the transparent one is slowly moving to transforming to violet color. Actually, this color actually. So the color over here. This color it is becoming this color. Okay, this was recorded with a high speed camera.
It is not visible, sir.
It's not visible.
No, no, no.
Just a minute. Let me show you again. So
Sir,
now
kindly
this.
zoom it, sir. Sir, kindly zoom it,
Huh?
sir. Sir, zoom it.
Well,
Only
then
the video
now
is
I
not.
have to make it bigger. Okay.
The things are placed not visible, but only I heard your lecture.
Okay, let me see this one. I escaped from the PowerPoint mode and just showing you. Okay. Now, initial stage. This is colorless, right? You can see this color.
Where? Not in the screen, sir.
Huh?
You cannot find the actual interest in the smart material that we
Yes, sir. Yes, sir.
develop
Yes, sir.
after seeing the actual practical.
Sorry, I could not understand your question. What is the question?
My question is just if it is visible, then we gather interest about your
Yes, it should be visible. Let me start again. Can you see the screen now?
practical.
Yes, sir. Yes,
Can
sir.
you-
It's visible. Yes, sir. Please continue, sir. It's visible.
Can you see the screen now? Okay, so this is the initial stage. Okay, now I'm starting the video and you can see the change now. It's getting dark, right? It's getting violet. I think it's clearly visible now. Is it okay to see? I mean, can you see the change?
Yes, sir.
Okay, great. Okay, let me proceed in the next slide then. So these are the material. Sorry. So this is the next slide. So here is one few more examples of photochromic material. You can see in this scientist, which is a Chinese scientist, who developed a zinc complex, which when you irradiate, this is the initial color. You can see over here. When you irradiate with UV light, it can changes it color. I mean, it's a 405 nanometer light, very close to the blue light. So it can change the color slowly become dark. So that is in solution state. But in solid state, those are completely different, and the application is more. As you know from the right side picture, also the normal lens do not change their color under UV light, but the photochromic lens changes their color in response to UV light. Okay, so next one is this one. So this material is photochromic material. So once you irradiate with the UV torch, you can see how this glass is changing its transparency and the color. Because of the changing color, it's losing its transparency. Okay, so you can see over here. And utilizing this principle, this photochromic material, you can even change, you can even write. The photolithography technique is very much popular nowadays. And you can see how the photochromic material, which is coated on the surface of the paper, and then you can just simply take a torch, laser torch, and then you can write on the surface. Okay. So these are the different applications. There are many other applications I'll not possible to talk about here, but more important is to understand the mechanism. I mean, and develop the mechanism. So there are different mechanisms being developed every day with different property. Okay, so and depending on their property, their application is different in different field. Coming to another interesting material, which is electrochromic material, which is electrochromic means the chromism because of the electrical potential change. Okay, and these are mainly very important for smart window. Smart window means, let's say you have in the morning you have a transparent glass, and in the as the day goes on, when the intensity of the sunlight increases, you feel that the heat is coming, and then what you do, if it is a smart window, you increase the potential. Just switch on the potential. I mean, switch on the switch on the current generation, and then you can increase. You can change the transparency of the window. You can see from this side. So this is the initial stage and this is the final stage. And there are many organic and inorganic materials which are available, which can show electrochromism in electrochromism as a result of applied voltage. So this voltage is not very much. It's 2 volt, 3 volt, not 220 volt or something like that. It's very small voltage you can apply, and then it can change its color. So these are the inorganic material, the nickel oxide, tungsten, titanium. All those things are also used as an inorganic material. In organic counterparts, polyaniline, polythiophene, even conjugated benzene rings are also used for electrochromic materials. So what they do. Once you apply voltage, they either electrical oxidation. I mean, they can undergo either oxidation or reduction in a result of applied voltage. So here are some videos over here. You can see the smart window. What you can see over here, it's developed by the different scientists. This is a Chinese university. You can see this is the 2 electrodes over here, and this is on the ITO glass. And as you apply the voltage, the film become blue. I mean, very less transparent. In the below video, you can see over here, the video below over here is also, you can see how this is changing color. Slowly it is changing color from transparent to green color. Okay, and utilizing this same principle, you can even write electrochromic writing. You can why it is not on. Somehow video is not. Okay, now I can see. So you can see this is one electrode, and another electrode is attached here with this hand, and another electrode is here. So as you apply voltage on the surface, you can see there is a change in color, and because of the color contrast, you can see the writing. So that is how the electrochromic material can be applied for different application. Okay. Now coming to another interesting material, which is shape memory material. All of you probably have seen some of in order to increase your beauty, increase your beauty. What you do, you put the metal. What is that called? This kind of metal braces in your teeth, because your teeth sometimes displace from someone is inside, someone is outside. So in order to make them in an order state, the doctor suggests this kind of braces, metal braces, for many of you. Probably many of you are using. Now going back to the previous slide, so this material is nothing but a shape memory material. What is shape memory material? Shape memory material are a kind of alloy material, which is nitinol. Either it can be nitinol, it can also be steel material. Steel, which is alloyed with carbon, also shows shape memory alloy. But most interesting or more commercialized one is the nitinol, which is an alloy of nickel and titanium for 55% and 45%. And what it does, it actually show kind of solid state phase transition in 2 different temperatures. Once you increase the temperature, it goes from austenite to martensite phase. And during that transition, it shows the shape change. So whatever the shape of the initial phase, it can remember, and once you increase being back to the temperature, it will come back to the initial stage like that. So let us see that one video. So let's see this video, what you can. Sorry. So this is a clip which was made by nickel titanium alloy, nitinol alloy, and it has been given a shape like this. Okay, and at a particular phase. And then if you deform this shape, once you start deforming this shape, what it will do, and then if you change the temperature, it will originally come back to the original stage. Okay, let's see this video. So this is the clip, two clip which is made. One is spring, another is clip. So and now what it will be done? It will deform the clip. Okay. So this is a particular temperature. That means it is in a particular phase. And now you put it on a hot surface to change the temperature and change the phase. And once it come back to the phase, it will remember its shape. It will take its original shape. So that is why it is called shape memory effect. And I'll tell you the mechanism in the subsequent slide. This is a metallic counterpart, I mean metallic material, which is nitinol. Okay, so this is how it will bring back to its original shape. Now, similar material has also been developed in as a organic material. Organic polymers also show something that kind of shape memory. You can see from the bottom left videos over here. You can see how it is not playing. Okay, I think it has some problem, coding problem. So you can see it, the right side and also the bottom right. At the bottom right, you can see how this shape memory polymer also changes their shape as a result of change in temperature. So it's going back and forth once you increase and decrease the temperature. So it's changing their shape. Okay, and based on that, you can do weightlifting. You can do many other applications utilizing this polymer or metallic material. And this one, the teeth basis one, which is shown over here, So it actually works in this mechanism. So this is at certain phase. You can see how the phases are changing, austenite to martensite when you start heating them, or when you start cooling them. So this is one phase, and in that phase, if you bend, it is deform shaped. And then if you start heating, that means it's coming from martensite to austenite phase, it will again try to come back to the original shape. So it is heated at particular, it is bent at particular temperature, and then you put it on your teeth and then leave it for coming back to the original state or original phase. And when it come back to the original phase, that means it will try to straighten itself, and as a result, it will pull your teeth and make them align together. So that is the chemistry behind your teeth braces. Okay, so recently one scientist from New York University, Professor Pansanam, also reported a crystal which also shows shape memory effect. That means the crystal, if you bend the crystal at particular temperature and then again you start cooling it, it will come back to the original state. Let us see this video over here, and that is because of the structural phase transition. You can see the structure is changing over here. So once you start cooling, so this is the cool stage, and then it bends, and again if you start heating, it will come back to the original state. Okay, so that is how the shape memory crystal works. Now coming to another interesting part, actuators. Okay, what are actuators? Now in the nature, you can see many actuators in the natural. I think I have to move fast because there are not much time there. Actuators. So what are actuators? Actuators are the material which can transform any kind of external stimuli like heat, light, electrical, and heat, light, moisture, pressure, chemical energy to mechanical motion. So they can change their shape, they can actuate themselves. They can change their shape, jumping, or linear motion, rotary motion, or even volume change, etc., etc. And in nature, there are many actuators. As if you see closely in nature, you can see many actuators. So the first panel, you can see the sprout, corn sprout, which when you irradiate light on them, it can show different kind of actuation. I mean, they actuate towards the light. This is a clove plant. Clover plant is nothing but a susnisa, we call it in Bengali. So in the daytime, you can see, in fact, many plants do like that. In the daytime, they expand their leaves in presence of sunlight, but at the night time, they fold themselves. Okay, they contract themselves, they fold themselves. The greatest example is sunflower plant, and they always move towards the sunlight. In fact, there are many nature and science paper which has been investigated to explain the mechanism of sunflower motion under the sunlight. I will show you in the subsequent slide. Another interesting, you can see over here, is the Venus flytrap. You can see the fly trap. That means the plant can trap the fly or any kind of material once you start pressurizing on the leaf. So they have a pressure sensor, and their shape is something like that can very rapidly, they can close their lips. So these are different types of actuation. So this is Mimosa pudica, nothing but a Lojjapati lata, we call it in Bengali. And then once you touch them, because of the change in turgor pressure inside the plant, it changes their shape. That means they contract themselves, they squeeze themselves, and here is one more plant, which is Silaginella lepidophilia, which changes their, they can actuate themselves in presence of moisture in their roots. The hygroscopic actuation, so hygrostimulated actuation. So it's very similar to the light stimulated actuation, or light stimulated bending. You can see over here. The stems are curling and all those things. So artificially, we have developed, in fact, this was my research during my postdoc. I can show you something, just one to slide, that these are thermally responsive actuating material. Thermally, that means when you start hitting them, it expands like a spring, and because of that spring kind of motion, they start jumping or different types of motion. So as you can see from the first video, it can slowly expand, it can jump, it can show earthworm kind of motion, or also it can also jump from here, it can also show breathing motion, something like that. Now the mechanism is why crystal jump. Does all crystal jump? Not really. Only certain types of crystal, out of 100, only 5 crystal jump. And that jumping can be of two mechanisms. One is rocket principle, that means the propulsion of ejection of material, like you eject the gas or any kind of thing, so that according to Newton's third law, it moves toward the opposite direction. So that is one principle. Another principle is like amoeba principle, the way amoeba moves from here and there. So because of the structural change or shape change, so once it's shape change happening, it can store the elastic energy, and that can be converted to kinetic energy. In fact, after several, I'm not going to the details, I'll just briefly summarize that these jumping crystals are a result of structural phase transition, which is very similar to the spring-like expansion. Over here, you can see over here, spring-like expansion in a very small period of time. Now imagine if you contract the if you take a spring and squeeze it and release very fast. So what will happen? Spring will jump. So it's the same thing is happening over here. Okay. So how much time I have? I might have to skip some slide probably. Somadip, how much time I have? Hello.
Sir, around 15 minutes you may take.
15 more minutes. Okay. I think that will be sufficient. Okay, so now coming to really one of the most bio-inspired invention. All of you probably know this material, which is Velcro. In your shoes, or even in your clothes, or even in your bags, school bags or official bags, you use this material, Velcro. Now there is a story behind this, how the Velcro was invented long back in 1941. When a Swiss electrical engineer, he's not even a chemist, he's an electrical engineer, George de Mistral, he went for a walking to the nearby seaside. Okay, and with his dogs. he has one dog. With his dog, he was wearing a woolen coat. In Switzerland means obviously to do winter, and he was wearing a woolen coat, and he went to the nearby seaside, nearby hillside, with his dog. And what he saw when he came back, what he saw, there are certain seeds, which is called burdock seed, which is generally found in the. So these are also found in our somewhere in our place also. You can see the spiky seeds. So some of those seeds are attached to his jacket as well as the dog's hair. So that actually really surprised him. What he found, what he thought, that why these types of seeds are attached to that, and it's very difficult to detach them, or difficult to remove them. It's really strong addition. And but there was no kind of liquid addition kind of thing. It's just a physical, physical addition. So he was really wondered, and he started inventing in that. And what he found, that there are small kind of spikes on the surface. So these spikes attach to the surface of the woolen or even jacket surface. So they have a kind of hook and loop. So based on those structures, he has invented in 1955, almost 15 years later, he invented this Velcro, which was patented by him, and after that it was developed in different way. So that was one of the most important discovery in human, mankind. Now another important inspiration is the gecko, যেটাকে আমরা বড় টিকটিকি বলি. Okay, so this animal, I mean this insect, we can say, can easily climb to the wall, right? So they can climb with defying their gravity. They can. So how they can defy their gravity? What is there? Do they use any adhesive, or they use something else? Now that was a long story, and I am not going to tell everything. But what it has been discovered very recently after the scanning electron microscopy was discovered, that their leg is made of different kind of settle array. Settle array means very small kind of hooks, or which those are called spatula, and they can engage themselves in van der Waals interaction. Now van der Waals interaction is very weak interaction. Everybody probably know, those who are master student or undergraduate student, probably they have read van der Waals interaction, what it is. Now van der Waals interaction, in a single sense, it's very weak interaction, but cumulatively they are very strong. When many interaction happens in a single in a confined space, then it becomes very strong. And because of the van der Waals interaction between the surface as well as the feet of that gecko, it can stick to the wall of that wall, and it can defy the gravity. And that force is so strong, it can defy the gravity. But that is possible because of the low weight of the gecko, but it may not be possible for the higher weight. But nevertheless, this was the explanation. Sorry for the sound behind. So this video was given by a science paper
called CT, and each of the CT is covered in even tinier bristles called spatulae. Their tiny spatula-like shape is perfect for what the gecko needs them to do: stick and release on command. When the gecko unfurls its flexible toes onto the ceiling, the spatulae hit at the perfect angle for the van der Waals force to engage. The spatulae flatten, creating lots of surface area for their positively and negatively charged patches to find complementary patches on the ceiling. Each spatula only contributes a minuscule amount of that van der Waals stickiness, but
okay. And based on that principle, there are many trekking shoes which have been developed, and which has been developed utilizing the technology which is adopted by the gecko. Okay, so that they do not slip on the surface when you are going for trekking. And in fact, you can sorry, this video, this shoes needs to be, okay. So in fact, there was a video which probably you have seen in Mission Impossible 4, where Tom Cruise was riding through the wall. And this was the first demonstration at MIT, how you can use the gecko's principle to climb the Well, so you can see in their hand they have a gecko's feet. So gecko's feet is over here. So they are just holding it on the surface, plain surface, and based on that strength, it is actually climbing over here. So the gecko's feet is not over here. This is connected to this feet. You can see there's a long rod over here. So technology is developing following the nature's principle. Now coming to another interesting material, which is superhydrophobic material. Superhydrophobic material is another smart material which is very much relevant in our, our life. As you have probably all of you have seen, all the students, I will ask you to see how the lotus leaf catches. How the water droplets behaves on the lotus leaf, or even the taro leaves. Taro leaves means kochupata. Okay, so you have probably seen, so when the droplet falls on that, it actually jump out. I mean, it do not wet the surface. So what is the magic of that surface? But other leaves do not behave like that. And until unless the ACM, scanning electron microscopy, was discovered, this could not have been seen. So you can see the spikes over here, and these spikes actually helps water droplets not to condense on the surface. And one of the parameters which described whether it should be hydrophobic or hydrophilic surface, which is the contact angle. I mean, the angle between the water droplet and the surface of the material. Now, if the angle is less than 90 degree, then it is hydrophilic. But if it is in between 90 to 150 degree, it is hydrophobic. And if it is more than 150, then it is super hydrophobic. That means it repel water. Water droplet falls on it and just jump out from there. Okay, let me show you the one video. Before that, there is a question for the students. All of you probably wear different types of fabrics, a cotton fabric and a woolen fabric. So when you put a drop of water on the cotton fabric, what happens, and when you put a drop of water on the woolen fabric, what happens? So based on that observation, can you tell me which one is more hydrophobic? So I'll ask you in the last after the talk. But before that, I'll show you some video how the water droplet falls on the hydrophobic surface and how they behave. So this is a high-speed recording, because it is not possible to capture with a normal camera, which is 60 frames per second. It has more than, the camera which was recorded is more than 1000 frames per second, high-speed camera. Okay, so this is how the water droplets. So you can see water droplets are not condensing on the surface. They are just repelling. Surface is just repelling from the surface. And what are the applications? So, but before that, let me tell you, there is another biological insect which also utilize the same principle, hydrophobic effect, in order to actuate themselves. So all of you probably know, in the pond where the sunlight barely comes, the smells are coming from the water or something like that. You can go over there and see there are some insect which is jumping from water. These are water strider. Okay, and this water strider has a tremendous technology to jump from water. Is it possible to jump from water? It's not really possible, because when you want to jump from somewhere, you need to have a solid surface so that you get the tip force according to Newton's law. Okay, so you should have the tip force so that you accumulate the potential energy, or potential energy, and that can be converted to kinetic energy. Now this water strider, you can see the video from here. They can jump from water. So how they get the tip force? So in order to jump, they need to get the tip force. Now, the recent is there are 3-4 nature paper with this. I'm just putting one reference over here, one nature paper and another science paper recently came up. That they have investigated that their legs are specially bent, and which gives you the more repulsive force to the water, and also their legs are covered with a super hydrophobic coating. This super hydrophobic coating means they have a repulsion between the legs and the water. So because of the repulsion force, they get the tip force from there, the surface force, surface tension force over there. Okay, so they can vertically propel. And based on that, recently one artificial strider was also made. So this is not natural, this is artificial strider, utilizing the same principle. Okay, so if this goes and this can be scale up, there can be many vehicles that can jump from water. Okay, just stagnate and then jump from water, utilizing the same principle. This is the technology is being developed slowly. What are the other application? As you can see, this shoes, the right hand shoe was coated with superhydrophobic and the left hand was not coated, and you can see the difference when you jump into the mud. Okay, so you can see the difference. In the right side video, you can see one is coated with hydrophobic, one shirt is coated with hydrophobic, another shirt is not coated with hydrophobic. So this page is coated with hydrophobic material, and you can see how they behave. The page is not getting wet, whereas the next page you can see how this behaves. So this is not coated with hydrophobic material, and this is getting wet. Okay, I'll just forward this. Yeah. So there are many applications that can be found from there, and in fact these are also used in marine vehicles in order to reduce the drag force underwater. So when a marine vehicles moves, there is a frictional force with the water which actually restrict their acceleration. But if you coat with a hydrophobic material, the drag force is reduced, and as a result they can move faster. So you can see that the left hand side had the coated one, the underside is coated with hydrophobic water. And also this hydrophobic material can also be used as an anti-icing surface. Anti-icing surface means, so in the cold countries, you can see this is the common phenomenon in the winter. Now if you coat with hydrophobic coating, so they will repel the water, they are or also ice, and it will this will not be so much icing on the surface. So these are the different applications. I think with this I will one more example I will finish. One more example, I think we have 5 minutes more time. This is another smart material which is touch me not crystals. So previously I have shown you what is how the mimosa pudica, I mean Lajjapati lata behaves. Once you touch it, it contracts itself. But in contrary to that, this is a crystal which has recently been developed by a Chinese scientist. Once you touch it, it will expand. It's very erotic behavior. And you can see over here, and the mimosa pudica I have already shown you, but you can see the videos over here. You can see once you touch it, it will suddenly expand. In fact, even the other one also you can see over here. It expands more than twice of its original length, and that is because of a structural transition, which has been shown over here. Structural transition which has been shown over here. Okay. Coming to, I'll skip the humidity-driven actuating polymer. These are the polymer which shows actuation. I mean, they actually actuate themselves or changes their shape or changes their places, move from their places because of the humidity gradient. Okay, you can see from here. So how these films are moving on a wet filter paper surface. Even they can move in presence of the humidity which is present at your finger. You can see over here. Yes, you can see on the finger, on the palm, whatever the moisture present on your palm, it can move with that. It can utilize that humidity gradient, and it can actuate themselves. But if you keep it in the dry area, it will not actuate over here. You have already seen that, and that is because the scientists have utilized the concept of hygroscopic material. I mean, there are different materials which can absorb moisture and changes their shape. So based on that, they have. So I'll move a little bit faster. Now coming to the light briefing, so that I have already discussed a little bit. I'll just show you one slide that recently has been developed. You can see over here how it is response to UV light and visible light, and based on that, they have developed a light-driven motor. So this motor do not need oil or any kind of electricity, just to irradiate light on the belt, which is made of polymer, photoactive polymer, and it will start rotating. So this has been recently reported in 2009 in a different paper. You can even see different other example also, how the light is rotating the micro machine over here. And the Venus fly type I told you over in the previous slide, you can see the light driven fly type is also there. Light driven fly type means in presence of light they can actuate and they can catch objects. So this is kind of light driven fly type. So with this, I think I will move forward just with one last slide, probably this one. And this one probably you know, this is a tendril, cucumber tendril. শসা গাছ বা কুমড়ো গাছে যে tendril দেখা যায়. And these are actually a wonderful phenomena, because this can be chiral, either left-handed tendril or right-handed tendril, or they can be expanded, they can be contracted. So recently, one Dutch scientist developed a photoactive polymer material by which she can mimic the motion of this cucumber tendril. You can see over here, this tendril is the polymer tendril is expanding upon illumination of the light, and the other one which is compressing upon the illumination of the light. So two different phenomena is she has developed based on the photoactive polymer. So I'll not go into the details about the fundamental over here. I'll just skip these slides. And recently we are also working in the similar area, the light different photo actuator. This is actually our research. This is actually our research. We are also partly working on the light-driven actuators, light-fueled actuators, and I will show you some videos from our laboratory. As you can see from here, the small crystals have started moving, and in fact, these are actually light-responsive material, either adjuvant material or different functionality which undergo geometric isomerization once you irradiate the UV light. Okay, these are some other videos you can see over here. The single, it's little dark because it's fluorescent crystal. That's why I did not put any other light over here. But you can see the movement clearly. You can see very clearly. You can see that. Sorry, very clearly you can see the movement, I guess. Right? Okay, so with this, I think I will conclude. I would like to thank my students who have really worked on that, and finally, I would like to thank you all for your attention.
Okay. Thank you very much, Professor Panda, for your deliberation on the very emerging topic and its application to the industry. Thank you very much. Just I am asking to the participants, if you have any query, you can ask few questions on the particular topic. Okay. Just we can give you only.
There is one question from Suranjan Haldar. Sir, what is the difference between superhydrophobic material and nanomaterial? Is it same or different? No, it's not same. The superhydrophobic material may not be nanomaterial. Okay, nanomaterial is of nanometer size, but superhydrophobic material has to be certified by the contact angle of the surface with the water droplet. Whether it is nanometal, but the surface is the nanostructure. That is very important. The nanostructure of the material is very important. That actually gives the property of superhydrophobicity. But if you say if those are same or different, then I will say it's obviously different. Nanomaterial is a general nanomaterial which have the size in the range of nanometer, 10.1 to 100 nanometer or even more than that. But superhydrophobic, the definition of superhydrophobic is that the contact angle between the water and the surface has to be more than 150 degree. Okay, that is, and it will obviously repel the water. Am I clear to that question, Mr. Suranjan Haldar, Dr. Suranjan Haldar?
Yes, sir. Thank you, sir.
Okay. Any other question from students or faculties? If you have any question, you can even send me to my email ID also. I am just sharing in the chat box. Okay, I think there is no question. Yes. Should I stop presenting then?
Okay, sir. I think there is no question from the audience now.
Okay.
So thank you very much, sir. Thank you very much, sir, for giving time.
Thank you for giving me the opportunity to talk to all the students and in front of all the faculties. Thank you very much.
Welcome, sir. So just I like to request Dr. Komalika Tiwari to address our next speaker, Professor Mishra. Before that, I like to say welcome, Professor Mishra. Welcome. Hello, Professor Mishra, sir.
Hello.
Okay, sir.
Somadip, Manusda may be saying something.
Yeah, just to say that I have to leave because I have an instrument booking today, so I have to leave. Sorry for, I hope you will not mind. And Nimai, I'm sorry that I will not be able to listen to your lecture. I'm sorry
Okay.
that I'll sometime.
Yeah, we'll get n number of occasion.
Yeah. Okay, and see you all. Thank you very much. Thank you very much.
Thank you, sir.
Have a good day.
Okay, sir. Thank you. Dr. Tewari.
Thank you, sir. Good morning to all of you. Honorable Speaker, Director, sir, faculty members of Dr. B.C. Rai Group of Institution, and our participants of today's one-day webinar on engineering of smart materials, laboratory to application. Before starting to our next session, today I would like to introduce to our today's speaker. We have today with us Professor Dr. Nimai Mishra. Let me introduce you all to our speaker, Professor Nimai Mishra, sir. He has awarded PhD from National University of Singapore, NUS, in the year 2013. He was a postdoctorate researcher from Los Alamos National Laboratory, USA, from the year 2013 to 2016. He also worked as assistant professor at Instituto Italiano di Technology from the year 2016 to 2017 at Italy. Presently, he is associated with Adhesive University. The domain of research is cell semiconductor nanocrystal optoelectronic device fabrication, and also is author of more than 20 journal papers. Sir, I'll welcome you on behalf of B.C. Rai Group of Institutions for today's webinar. Sir, please continue.
Thank you, Dr. Tiwari. Yeah, let me share it now. No, no. How do I get? Once again, we have been using Zoom, so I'm not frequent in this Google Meet. Shall I present now, share screen, or what shall I do?
Yes, present now, then share screen, and you will have the option of present in a window.
A window, right? That is coming. Yes, great. Thanks, Omudi. Yeah, I think it's completely visible, right?
Yes, it is visible right now.
Yeah, okay. Thank you. First of all,
Yes, sir.
Namaskar, good morning to everyone. Somaike Natun Bochhorer onek shubechcha. I believe everyone understands Bengali is here. And thank you so much to the director, sir, Professor Roy and Professor Ghosh, and my junior, my good friend, Mr. Somadip, who actually invited me to give this presentation seminar on this particular day. Somadip and myself belongs to the same hometown, Katwa, nearby to Durgapur. And I think Somadip is junior in my school also. We have been in touch for a long time. So I'm very happy that when somebody asked me, Nimaida, can you able to give a talk? And then, yeah, I have been doing this kind of popular science talk for a long time. I love to interact with the students. So somebody when asked, definitely, there's no hesitation. And hopefully, in near future, if things got normal, love to visit physically. So that's given more, interactions with the students, and we can share our different findings. It's more joyful mode, so student can understand, and we can find it out more implications in the physical mode. I can look for that once again, organizers and Thanks to Ms. Thakur for kind introductions. And he's also senior of me, and then we have been also in touch for a long time. He has given a good talk of different materials. We have been talking today engineering smart materials. As I informed from Somodeep, I think the students are mainly engineering background, not mainly, yes, all engineering background. Am I right? They are BTech student, correct? All are of them BTech. BTech, is this BTech civil, mechanical, computer, or any or any
Mostly are from BTech.
BTech? Yeah. Is there any MTech students? Right? No.
Yes, few of them are there from the MTech, and also some research scholars are also there.
Okay. Yes, our research scholars also there. So very good. But the talk is mainly keep an eye on the BTech student. But definitely it will be useful for masters and some of the early career researcher. We are going to share some of the recent findings, not in my laboratory, our lab, but I have been working in this area. And as you know, as a chemist, as a researcher, we have been working in the fundamental aspects, and then it is the engineers like you guys who can take forward these fundamental aspects of the sciences, and you make these applied sciences, and you bring the product to the society. So some just similar kind of story I'm going to share with you guys, and then I have entitled the talk semiconductor nanocrystals, which is like a nanomaterial. I'm going to discuss about the laboratory to industry, display industries. Okay, and it goes along the theme of today's webinar, which is engineering of smart materials and the laboratory applications. I think all of us who's understood the importance of smart materials, I think we have understood this thing much more than before, particularly in this pandemic, when everyone is looking for a smart molecule, which is a smart material that's going to inject in our body and that's going to save us for this deadly virus. Anyway, I believe this virus is no more deadly, but still, if we're having comorbidities, definitely it will have going to have an effect on us. But that's the smart molecules, everybody, smart materials, people are working through it. Now, it's a very pleasure for us to give this kind of translational science talk to the engineering community. Currently, I've been working as a assistant professor in a university, which is main focus also engineering, but don't have a very strong sciences department, strong science research going on. What we have been observed in my observations all these years after staying abroad, that mostly in India, so we have been doing, many of us, I think many of our faculty members, researchers are doing wonderful jobs, but we able to restrict ourselves within the boundaries. Because I am a chemist, so I thought, okay, we are the champion, we are the best. Physicists think they are the best. Engineers think they are the best. Computer thinks, okay, mechanical no use. Civil said, okay, we build everything. So this kind of hierarchy going on, and we are sitting in silos, and that makes ourselves completely, restricted ourselves to go for out of the box thinking, and then that's actually restrict our ability to find out something very innovative that's going to change the world. So this thing is not there if you go out there in the Western, mostly in all those universities. I was graduated in NUS, National University Singapore in 2016. I believe in 2013, in believe it or not, before I went to Singapore, I was kind of in dilemma because I got a position to go to Germany and then also got a very good positions for scholarships in Singapore. But Singapore was not a place to go for a higher education because it's a place for honeymoon, right? Travel. So I never thought about it so seriously, but I dig it out. I talked to many of our seniors and my professor at IIT Madras. I was doing masters in IIT Madras, and finally I take a call to go to Singapore. But it came out beyond my imagination. This small tiny country make these two universities, NUS and NTU. They are now world ranking on 11th and 12th. They are as comparable MIT and Harvard. Only things are lacking. They are not able to get the Nobel Prize, which is MIT. The small town of Boston is the MIT and Harvard. They together produce 100 plus Nobel laureates. Maybe that's how this culture, because no university cannot be overnight, can produce that kind of Nobel laureate. It takes hundred of years. Harvard, Oxford, there's a 300-400 years old university, and they got this culture. And that kind of culture we need it because there's no boundaries. I was in chemistry. I was taking a course in electrical engineering. I was working in a colleague who was graduated in mechanical engineering, then doing PhD in material science, and then working with us in a chemistry laboratory. So you can imagine how interdisciplinary world is, because it's completely. So that's the I think I'm talking to these young people, the BTech people, soon after you're going for a job or you thought about some higher studies, don't confine yourself in these silos, these boundaries. Keep open your eyes, try to open for collaboration, talk to your colleagues. Okay, don't think, okay, this is the best, oh, I know the things. No, not like that. You know, if you think about all this together, then all you can progress. And that actually right now in this pandemic is taught us. Again, it's showing, how a good teamwork, okay, a bunch of chemists working with bunch of biologists in the presence of medical doctors and biotechnologists, correct? And that's how this vaccine is going to come out soon. So it's a proper example how the teamwork, how the interdisciplinary research can save the world. So in that direction, we're going to share some of the very interesting findings that people have been working and that you guys already knew. Many of you heard about it. I'm going to show you some of the nanomaterials, which is also part of like smart materials. And we are, as a chemist, have been engineering those smart material in the nanoscale level in our laboratory and producing this beautiful material, and that you are having on your hands now. So currently you are using these electronic gadgets, the smartphones, okay, these LED TVs that are having this kind of smart materials. So I'm going to show you. So these are the picture. You can see very colorful picture and giving light. This is called fluorescence light. If you shine UV light, what Manusda was showing under UV light, colors is changing. It is on the same directions. When put under UV light, depends on their nanoparticle sizes, we can get different color of the nanoparticle. And this color people have been using for displays, all those gadgets like mobiles, in the televisions, in the iPad, all those things. So that's the story of today's talk. And first, one more thing is almost 11:30. I promise you guys, it's very difficult nowadays to hear more than an hour. You have been hearing from 10, 15 from Manusda, and then it's very difficult actually to keep essence. I try to be short as much as possible. I just try to give you a very brief essence that how this smart material, which is nanocrystals from laboratory to industry. So let me give a few seconds where from I coming. This is a new university we're building here at the capital of New Andhra Pradesh. After Andhra Pradesh got bifurcated, the Hyderabad goes to Telangana as a capital. So new capital is Amravati, which is in Vijayawada. Many of you may heard or pass through Vijayawada when you go either Bangalore or Chennai. That rail train goes through this wonderful junction, and there we are building. In 2017, upon call from AP Chief Minister, then Chief Minister Chandrababu Naidu, they have given a 200 acres of land of SRM Group. I think since you are from engineering background, all of you might heard of SRM Institute of Science and Technology, SRM Chennai. So this is same SRM Group, but they built it completely new university. So this is a huge construction. We have built it within the last 2 years, and we have been able to catch very good faculty members with the world reputed faculty members. Our goal is to make it very research intensive, interdisciplinary research. There are liberal arts in the curriculum of the engineering students, science in the curriculum of the engineering students. A science student can take a minor in engineering curriculum. So that's, and also we have a very strong research program. Let me get the, there's a pointer. So my office is somewhere here, I'm sitting here. And it's a very mammoth building, you can, and there are hostels block. Inside we have recently constructed X labs when our research labs are located. I'm going to show you some of those. So I certainly welcome particularly Somodi, Professor Ghosh, okay. And kindly, whenever you are coming this side, just give me a call. We're certainly happy to host you guys. So today's talk is mostly like popular science talk for these young minds, but this is kind of overall summary of what I have been doing in the last 10, 11 years as a research, starting from my master's in IIT Madras and then going to Singapore for my PhDs. I was Los Alamos lab in the US, which is one of the again renowned laboratory under Department of Energy of US government. Actually, that Los Alamos lab, many Bengalis has read the story of Narayan Sannal Biswas Ghatak. That's the lab where the first atom bomb was invented. So it's a blend of rich history, the laboratory with the Niels Bohr, Einstein, then the great physicists, chemists, they worked there to develop the atom bomb, and later on it's open for basic sciences, and now there are proper blending of basic sciences and engineering. because I keep focusing on this, because I have been teaching this engineering student here in SRMAP for their fundamentals material courses, fundamental chemistry courses. People are, again, what I emphasis, thinking in silos. I'm a computer scientist. I do not need damn. I don't give to any damn to physics and mathematics and chemistry. But no, you know as much as mathematics than anybody else, the computer people. And job becomes so interdisciplinary. If you want to do something out of the box, you need to know all this information, all this information. So that's a better open our eyes. That's the key focus, my key focus on that direction. So we have been working in this area, the semiconductor nanomaterials, for this last almost like close to now 11 years. We have been synthesizing. See them, definitely many of you have this experience when we want to see the C-section of any plant leaf under microscope. That's an optical microscope to enlarge it. But here the things are so tiny, nanoscale to 10 to the minus 9 meter, very, very tiny. And that goes, you need a microscope or source that, particular wavelength matching. So that's only able to do with the electron microscope. So this is called transmission electron microscope. We can see the structure. And then, of course, for the use of this material, because we can engineer this material according to our need. That's why engineering the smart materials, and then particularly for various applications, the photodetector and solar cell and thermoelectric. So these are itself are different branches of interdisciplinary research. I have been working all these areas, making photodetectors, solar cell, and solar cell. The silicon is best, but still we are making perovskite and 2,6 semiconductor solar cell that can reaching close to 15%. And advantages, I'm going to show you what is the advantage of a nanoparticle compared to the silicon I'm going to discuss. And a thermoelectric, and one of the most important area of research that's going to be already hot topic of research and going to be further funded by government and other private agencies, because we have been losing so much of heat as a waste. Whatever machine, whatever automobile things you're going to drive, or whatever machine you're going to running, you're going to lose almost 30 to 40% or more than that energy as a waste heat. So thermoelectric with the Seebeck phenomena, simple physics, if you convert this energy, again, nanoscale material has a huge opportunity to got those waste heat to again coming back to electric energy. So these are the dimensions we have been working. Now, particularly in today's talk, I'm going to discuss that semiconductor nanocrystals for light emitting applications. So what is light emitting? Light emitting diode. You may not know the full form, but but I believe all of you know, because since you are engineering background. So light emitting diode is like a LED. That's everyone knew about it. If you go to village, if you go to anyone who doesn't have that proper this kind of traditional educations, even though that person also know LED, because you can spot LED light on his or her home. So that's come, the LED is invaded our households. Almost we have been changing all those on those tungsten, all those lamps, all those carbon lamps with this all LEDs, and that's become households. The same 15-watt lamps can give same kind of illuminations compared to 100-watt that we used to use like 5-10 years back. So we're going to save the energy, and the light is more wide, it will be more proper kind of sunlight of ambient, you're going to feel it, and that's going to helpful, get good soothing for your eyes also. You're going to save energy, you're going to save electricity bill, so all sorts of things. That's why LED become household item. Now, why we should use the semiconductor quantum dots for light emitting applications? Okay, so this is because the solution process electroluminescence displays. So this is called electroluminescence. What does it mean? Lumination means you are getting a photon out, and electro means current. So you are giving a current and you're getting a photon. What is photon? It is a light. So it is the basic principle of LED light. You are switch on the light, you are giving electricity, and some light is coming out from that bulb. So that is the white light coming. So that's called electroluminescence. And when you put this kind of small tiny lights on your electronic gadgets, that's called displays. Okay. And these are made of semiconductor nanocrystals. So what semiconductor nanocrystals do, as I shown it in the very beginning slide, these are the material, the smart material, that can give different light emissions based on their sizes. How we can control that? So that's the engineering. So nano engineering of this material to get the proper emissions. And in a display, you have using all the VIBGYOR color, right? You have a red, green, blue, because you are watching a movie. It consists of color movie. So you have consist of all VIBGYOR, all different kind of colors. right? And then this material has been used for the next generation display technology. I'm quite sure if any of you nowadays is coming in the television ad, the QD LED TV. Have you heard about it? I think I'm sure many of you heard about it. This QD LED TV is quantum dot LED TV launched by Samsung LG. This is used this semiconductor nanocrystal. That's also called quantum dot. The abbreviation is QD. That's why it's called QD LED TV. It's nothing else, is the boon of chemistry and the proper blending of applications to interdisciplinary science by chemist and electrical engineer, and nothing can be done with the computer without computer. So you need a computer scientist too. So it's a proper blending of interdisciplinary sciences. So we are using the semiconductor nanocrystals as emitter, okay, for next generation displays. If you are passing through, I think airports, Indian airports nowadays is is very good, is very smart. Smart airports are passing through Delhi, Bombay, Hyderabad, even Calcutta also. I think I have spotted QTL TV in Hyderabad, in Mumbai, where you can, Samsung has been displaying the QTLED televisions. Okay, this is not yet reach our household because it's kind of costly. The materials processing still under investigation, so you need to optimize the cost. I hope soon or sooner or later the cost will be drastically come down, and then it will be a household product. Now, what's the reasons? This is a high efficiency, of course, that I mentioned. Any product you're going to buy it, you first see is how efficient it is. What does it mean? It means that I'm going to charge for a day. Let's say you're going to buy a mobile. What things you see? You see the how is the color contrast, how is the display, right? How is the battery efficiency? Let's say I charge for one day, how long to you're going to have. Okay, but anyway, those days are gone when you used to use this Nokia. One day charge, 7 days enough, because those are not smartphones. But now we are having all those sorts of all sorts of applications. We have been using the app, so definitely it's very difficult. But this is one point about interest. You're going to check the efficiency. The white color gamut. Okay, just give me a moment. Just give me a moment. My two kids are shouting like anything. I come back and just ask them to be yeah, just one second. Hey, aste. Okay. Yeah. So you can understand the school is not running, so they have been bored and confined like all of us. Okay. So then come back to so they have a white color gamut. So that's one of the criteria to choose or using material for LED lights. So this is materials having white color gamut, low turn on voltage. This is again something related to efficiency. You need very low voltage to turn on the light. So you don't need much energy. And of course, the low manufacturing costs. So these are the things that we can make material if you know simple chemistry, or no need to know chemistry even. If you can make a coffee or make a Maggie on your own in your hospital room, on your home, definitely you can able to make this nanoparticle. I'm going to show you how we're going to do that. Okay, so these are the salient points why this nanoparticle and why we can able to engineer this nanoparticle for these beautiful applications. Okay. So I hope we've given enough motivations why you use semiconductor nanocrystals for LED applications. The reasons are that. Now the second question is, why semiconductor in electrical devices? Why not metal? Why not the insulator? The reason is very obvious. This is a band structure. Again, I don't want to give any introduction about it. All of our aware of it, but still. Now, why semiconductor? Because we use a material that can control easily the conductivity. We cannot control the conductivity in the metal because they are highly, they are conductor. There are no obvious gap between valence band and conductor band. Every time, the moment they connected with the electricity, there turns, flowing electricity. Okay. On the other hand, the insulator, the band gap is quite wide, so it's very difficult to make it, conductor. Correct. But in between, we have a material that's called semiconductor. There is a band gap. That means without external force, it cannot conduct electricity, but you can make them conducting. How we can do that? So see, if you put the sunlight, or if you can apply some of the mechanical sources, the electron goes from the ground state to excited state and start moving. And when electrons start moving, that is the electricity, right? So that means we use semiconductor because we use a material that can control the conductivity. So based on my external forces, I can control the net conductivity. It is not too easy to control conductivity in conductors. Just now I said, now all the transistor, okay, see, all the transistor works as a switch. Okay, so that switch only you can able to get in the conductor, and these are the basic principle any of the electronic devices. So see how things are interdisciplinary. Chemists are working with the engineers, okay, and then electrical and engineers, okay, and at the end you need a computer support system. So that's how, and then this is not only chemistry, it's the physics too. So as like interdisciplinary nature of the work, okay. So we understood why you need semiconductor, why you nanocrystals, and then why is nano? We can use the bulk semiconductor. Why is the nano is important? So nano, as I often put, is a middle ground. And we Bengalis have a very, very strong connection is nano, right? If I ask what is nano, people will remember, recollect one of those incidents that happened in our lifetime. The Tata Nano car was there, and I'm not going to connect any politicals. Please pardon me. I'm just giving the incident that how this Tata bring the car, right? And so that's how the nano came to all of us mind. So what is that nano means? Nano means tiny. Tata was launching this very tiny car and they gave nano name. So what apparent nano mean? Nano means is very tiny. So same likewise, we are putting a material, this could be very tiny. So let us understand how the nano looks like. So this is something called macroscopic scale. The people you are and all of us, we can see each other, we can see almost like 100, 200 meters in our naked eyes. So that's called macroscopic scale. Whatever you can see with our naked eyes. Okay, then there's a galaxy scale. It is beyond our perception. Okay, we need lots of telescope to see those things. Then there's called microscopic scale. So like an ant, we can see the ant, but are you able to see the eyes of an ant? No, it's not very clear. You have to put those eyes in a microscope, optical microscope, then something looks like this. And then on the other hand, it's become very, very tiny subatomic particles. These are atoms, then molecules, these are inside the atoms, some are nuclear physics, okay, particle physics, the electron, proton, neutron. In between something is nanoscale. Okay, when few atoms comes together, it makes a molecule. When few molecule comes together, you make a nanomolecule, and that's the nanomolecule as point of our interest. So then a question remains, why this point nano is a point of interest? Why not a microscopic scale? Because whatever the property, because our theme of this or today's webinar is engineering the smart material for applications, and most we have been talking about electronic applications. And even if you take any kind of applications, it comes from the physical or chemical property. The physical or chemical property changes of a material when their electronic configuration do changes. So that's the basic underlying story of any properties. If you think all this, if you see the periodic table, the most important table people have invented so far, that's the periodic table. Okay, that consists all information so that whatever element available until today's date in the earth. So what is the periodic table? From the atomic number, the element's property changes. That's why oxygen is different than nitrogen. Nitrogen is different than sulfur. Sulfur is different than hydrogen, isn't it? So lead is different than silicon because of the atomic arrangement. So it is the electronic number that makes these changes. So if we see, when you put, let's say, one of the most beautiful molecules, present along us, within us, is called oxygen molecule, water molecule. So one oxygen atom and two hydrogen, they brings them together, make a water molecule, isn't it? So what happened? The electronic structure of water molecule is different than the electronic structure of a single oxygen and single hydrogen. It's obvious because they are bonded now. It's like they are becoming a family, right? Chemistry is like a family. Chemistry is like a love story. Yeah, they fall in love. They make a bonding. It's like a widow bonding. So they make a bonding. Okay, and they make a molecule. When they're extending love, they're bonding, they make a macromolecules. That means hundreds or thousands of atoms or molecules together, and that brings a nanoscale, and their electronic structure changes. And when their electronic structure changes, the mechanical, physical, and chemical property do changes, and that's how the nanoscale materials is so interesting for all of us. Okay. Now, why semiconductor? So I have given 3 motivations alongside my title of my talk. I'm going to use semiconductor nanocrystals for display. Then I have given why nanoparticle, why semiconductor, and then why semiconductor nanocrystal. Nanocrystal is nothing else nanoparticle. So semiconductor in nanoscale has many new interesting properties. Just now I said, when you make it in nanoscale, the property changes because the electronic levels changes, which can further improve the electronic devices. That's the goal of all of us, to make something useful for the mankind, correct? Okay. Now let us see, as I said, a few slides back, that you need to know of cooking of coffee or making of a, Maggie, then certainly you can produce these nanocrystals. But don't do in home. There's some safety and there's a hazardous chemical we use, but you have at least basic knowledge of cooking, you can able to do, the synthesis of nanoparticle. So making of synthesis of nanoparticle, we use a very particular chemistry that's called colloidal chemistry. And I often say that I'm a cooking chemist. Chemistry is not, it's like a cook. I cook. To be frank, my wife cooks very, very, delicious food. So I was always telling her that if you go to the laboratory, you'll be much, much better chemist than I, because you know the proper blending of masalas to make some particular dishes. So you know what is the masalas, nothing else, is the chemical. So chemists are cook, if you control, your mom may be very good cook, making very good biryanis. So that maybe your mom can be very good chemist too. She doesn't get an opportunity to produce this kind of, work in the laboratory, so you don't know. So it's nothing else, it's like a cooking. Okay, it's like a cooking, mixing of masala, similarly mixing of chemicals with a little bit of sound knowledge of background of basic chemistry, and then you can produce this material. So now you can cook here in this home setup. You have an oven, you have all those crockeries, but here in the laboratory, we have a little bit of different setup because we need a control environment. We can cook in open atmosphere, but it doesn't matter. In the open atmosphere, the cook is, the food is not going to change. But material we're dealing, if you make it in a humid atmosphere, open atmosphere, it may degrade. So we need a control environment. So that's why we're sealing it, and we are purging argon, which is the inert gases. And then this is a hot plate. Likewise, we are using oven, and this is the vessels. It's made of glass, like a crockeries this gentleman is using, and we mix the chemical like he's mixing chow mein or pasta kind of thing. So you can mix the chemical, you can heat it in a certain temperature. As simple as it is, if you ask you to cook rice, what you'll do? You take a rice, you take a water in the proper ratio, and you heat it. In that case, you need to bother about the temperature because now water boils at 100 degrees. So you no need to bother about the temperature. But in many cases, you need to bother about temperature in a cooking. Otherwise, you'll be over fry your item. Same wise, there is a thermometer here. We can check the temperature because depends on the temperature, we can make different products. So it's as simple as cooking, And then with the cooking chemistry, we're using the colloidal chemistry. What is the colloidal chemistry? It is also a basic, all of you have, in a summertime, have drank this sugar lemon juice. So if you take a spoon of sugar and put in a glass of water, they're completely miscible. And that's called true solution because the particle size is very, very tiny. Okay. And then you can't distinguish sugar and water. On the other hand, if you may put in a spoon of that particle or mud and then stir it, it will give a suspension. But sometimes looks like it dissolved, but it is going to settle down. Because the particle size is very, very, way higher than this sugar particle. So this particle cannot be suspended in water. Water don't have that much of force to hold it. In between, there are one kind of solution. They are not true solution. They are not suspension also, but they are stable for a long time. That's called colloidal solution. And their particle sizes are 10 to minus 7 to minus 5. So we use this colloidal chemistry and use these holes based on, I'll give an example like how we use the soap water. So soap can use to clean dirt of the molecule. It's like a surfactant molecule, and they form micelles. With this micelle structure, they have these microvessels, and these microvessels we use for grow the nanoparticle. We can discuss, some other day of the colloidal chemistry. So these are basic fundamental. The colloidal chemistry, we have a surfactant molecule like the soap molecule we have been using, and they have a hydrophobic hydrophilic end, and they have been arranged in the water like that. And this cavity is a nano cavity where we are going to put our precursor to grow nanoparticle. So that's how we can control the nanoparticle based on the choice of surfactant molecule, based on the temperature, based on the concentration. We can engineer this material. That's why I keep focusing on the engineering this material, okay? And I believe all of you can do that if I teach you for a day or give a demo in the laboratory, okay? So once we synthesize the semiconductor nanocrystals in this kind of setup, I have to see them under transmission electron microscope. They look like this. They are very tiny, less than 10 nanometer size. You can see very, very tiny. The scale word is 20 nanometer. I have been summarized all those things in invited book chapter that's published from US, and where we have discussed all different aspects of the semiconductor nanocrystal synthesis to applications. Okay, and then These materials, you know, as it's very tiny means very energetic. Okay, very energetic. So nanoscale material are very energetic. So we need a surface capping groups that makes them stable in solution. And this material, you can see they absorb very good amount of solar light and also give emission. So that's the most important aspect of this material. And based on their wavelength of emissions, we can able to get blue, green, yellow, orange, red emission. And these are the particle, you know, these are due to the quantum confinement effect. And how this quantum confinement effect, you take a bulk material, you go to the nanoscale, is the high school physics, E is equal to, I think all of you must know the particle in a box model, n squared h squared by ml squared. So it's inversely proportional to the diameter of the particle. So if you have a bigger nanoparticle, the band gap is decreases. If you have a small nanoparticle, the band gap is increases. So that means blue, and bigger particle gives red. So if we are able to tune the size of the nanoparticle, we can get the different color. Understood? So that's the beauty of nanoscale material, that you can able to tune the color, and then this material we can use for the display application. Okay, so we have understood all those things. Why semiconductor, why nanocrystals, why we need some nanocrystals, all those things we understood, how we can synthesize the cooking chemistry. And now let us understand and just give you a very brief info, and then we're going to connect with the LED. I'm going to end it in next 10 minutes or so. Okay, so semiconductor, there's a semiconductor nanocrystal. You shine a photon, and I think I'm going to skip all those things. Maybe the interest is this one. Okay, I'm inject the electricity, and then the electron and hole, they recombine, get a photon out, and that's called light emitting diode. So that's the point of interest. This is our nanoparticle, very tiny one. I'm injecting electricity, I'm getting a photon out. So that's the basic underlying principle, whatever gadgets you have been using in your hand now, the mobile, and you know, and hello, Shomadip, I'm audible? Hello?
Yes, sir,
Yes, sir. Audible.
Okay. So likewise, let's now come to that proper business. Okay, so we have understood the semiconductor nanocrystal. We also got to know that due to quantum confinement, we can able to tune their sizes, and based on the sizes and get a different color. Now, what are we going to do that? So this is the image taken from actually Samsung, their website. You can see they're able to synthesize very bright emissive, this nanoparticle. And this is the area we have been working on. My PhD supervisor in Singapore, he was working in a MIT as a PhD student, and his supervisor, along with some of his senior colleagues, they have gave a startup company in the early 20s, you know, okay, early 2000s, 2001 or 2, and that called Q Divisions, Quantum Dot Visions, and that Q Division later on collaborated with Samsung, and they have put forward this nanoparticle, and that's how we can see in the market the QT LED TV that is recently launched by Samsung. Likewise, LG also working parallelly. So that's how my connection with this nanoparticle. I have been working also in LEDs with this material. But definitely, when this QT Vision and Samsung, they are working, because you know we have been working the basic aspect, and when you go to the application aspect, they check more about the durability, stability, efficiency, cost, you know all those things. So they have developed their own protocols that should be stable. They don't share with anyone because they are under patent, right? So basically, it is the same way they have been synthesized, but they follow different tricks to make it more further stable, photostable, and they have integrated those nanoparticles in the LED devices and make this television. So these tiny nanocrystals can add above the backlight layer on the LED TV and another such display. When the typically blue LED light is shown through a layer of quantum dot, the crystal produces a richer white light. Because what is the white light? Even the white light, if you make a proper blending of blue, green, red. If you make a proper ratio of blending of blue, green, red, you get a white light. So that's the white LED is coming into picture. Okay, this light seen the results a better picture. Okay, now this is something. A simple schematic, okay, you may very simple. That's how LED has been formulated in the laboratory. We have also have been working on this. You can see this is called quantum dot layer. This is the layer giving the light, and this is the LED often see in the street light and everywhere. How they make it? There are electron conductor layer, hole conducting layer, and these are the electrode, and then we inject electron hole into opposite side, and then electron hole goes to this quantum dot, and they recombine there and they give a photon out. So that's the call basic, here in schematic I'm showing the basic principle of LED. Though there are many factors, I'm just showing a basic principle. There are many standardizations is need to be done. people have been focusing. There are people, researchers, who have been devoted their life to find out copper electron hole, injector. That particular theme of research. So that's how the research is intensive. That is one thing also lacking, some part of it. We have been in a system that drives us to find it out very fast solution. Okay, and yeah, that is fast solution. I don't know, means I'm not going to criticizing anyone, but that's how it is. The system is asking, okay, you give me product, you give me publication. So that makes us, particularly in our, academics, we're going to produce very cheap quality of publications. Rather, we have been focusing on a real problem for longer time. It's a system because, if you don't get publication, don't get a promotion. You don't get a promotion, you're going to stick on your job. You don't produce PhDs, you can promotion stuff. So all those factors are, there. Nothing wrong on that, but I believe in something in proper blend between you give a proper thought process for a more harder problem. You should get more longer time, sufficient funding over the time, then only produce, which is available in part of the Western, like MITs, Harvard, even NUS, Singapore, and Japan. They're following. In China also some sort of replica, the same thing. And India also, very good news in the recent years. We have been replica. There are wonderful centers of research have been developed. One of those is very right there, Indian Association for Cultivation of Sciences. The solo Nobel Prizes from India is from there. In Calcutta, the GCS Center in Bengaluru, and NCPS for Biology in Bengaluru. So all those places wonderfully. The young people, many of my friends, colleagues, are doing very great, So our culture is all changing, very changing. Again, I'm not criticizing anyone. We need a culture, something blend. We have something good within us, and we have to adopt something good that we have learned from other people. A proper blending could be, right choice, right choice. People, if you think, okay, completely make it in Western style, and that doesn't going to work because we have a demographically different country. Our nature are different. That's not going to work. But we need to know, I need to have some sort of their good practice, and then within us, and then we have to inculcate, and we have to focus for longer time. MIT become MIT all these 300 years of effort. We have the IIT, that's founded in 1950s. Understood? So we have a long way to go, but that too we have to support and substantial funding. Then maybe later on, I'm very hopeful, maybe Nobel Prize could be possible from our own soil. Understood? So that's the things. We have to take the good things and try to cultivate this into disciplinary research. We all have been shocked. What happened day before yesterday? Again, nothing to be political. Yeah, American people can do this. Honestly speaking, it is American people, they invaded their capital. We are illiterate people is much better than those people. So I'm not saying that you follow that thing. Follow their culture of science, that invention of technology, the merge with our knowledge. Definitely there will be a right choice. I can come back to this, today's talk. So this is the basic model. So we have to focus on the certain problem. Then definitely, I gave this all example in a connection that we need to focus in a harder problem for longer time, and that only possible substantial support, sustainable support from the institute and the government. Then only is possible. So once we have this QD LED TV, how this works. So this is our QD panels, and then this is the back LED light. This all information are available in Samsung. There are a number of YouTube videos. Those are more interesting technologies. So quantum dot technology is most successfully employed is LED QD because they are giving highly fluorescence, highly color pure. You can certainly see so mechanisms of the televisions are it is almost same as a OLED TV. Only we are changing the fluorescent material, which is quantum dot now. Now I'm going to show you a real picture how it looks like normal LED TV and how looks the QD LED TV. So this is a picture of a frog of in a normal LED TV. You can see the differences of color. Actually the frog has been found a deeper green color with a deeper red. Okay, but that cannot be seen in a normal LED. But QD LED can give you a very, very pure color, almost like a natural. This is not, actually 100% natural. It's not possible. Nobody can replicate 100% nature. The nature is the best scientist, best engineer, whatever we can say. But still, this is more closer than normal LED TV. Okay. So I'm almost end of this talk. So we have been, I think I have given very good overview that how in nanocrystals, semiconductor, we can engineer in the laboratory, in the cooking chemistry, make the material, and then integrated devices, and that's become now household, right, in your household. Advantage we have been discussed in the beginning of this quantum dot technology, high peak brightness, because the color is very pure, color saturation, color gamut. These are the technical terms when you charge a LED light. Low energy consumption, then everybody will understood because it consumes less energy, you will have a less electricity bill. Improved color accuracy is one more thing. The green is pure green, not like mixed with yellow. Ability to leverage existing supply chain. So basically, we can produce more this number of material, devices, and eventually it can go to their household. Okay. So why these things? Anyway, I'm going to, yeah. So these are my own research, and then I'm not going to discuss all those things we're doing here, but I'm going to show you. We have been working these semiconductor nanoparticles in here SRMAP. We are producing these nanocrystals, making LED devices. This is our own research that we have published with my PhD student in 2020 in a high impactful journal, published by Royal Society of Chemistry, and also published in the Wiley from Germany-based publications. We are also working on this material. It's a green emitting material for LED devices in the SRMAP. We also can blue emitting material and red emitting material. And currently we have been working on fabrications of LED devices. So also see, this is we put this material in the glass slides, and we can see their photo stability has been stable for more than a year. So that has been intensive work going on here. And so finally, the take-home message is here. When the pandemic came in last year, in 2000, it came in 2019, but it actually came to our household in 2020 March. When China was suffering, actually, I still remember that in last 19 December, I was thinking, oh, no way, it's not going to come to us anyway. No, we are very confident. Then later on, we are confident, okay, kind of atmosphere, there are studies are coming, and temperature, no, it's not going to come to India. Later on, there's Italy and Iran invited like anything, and still we are thinking, but it came to us, it came to our household. Many of my friends and family got infected. Unfortunately, I have not, but who knows? Maybe all of us involved, we don't know because it's become mild. But the take-home message in these days, in this tough time, we have seen that how doctors, how nurses, or engineers are responding to a crisis. That's the thing I have been talking. I want to emphasize to these BTech students because see how they respond to this crisis. Wonderfully, see, we as an Indian, they got n number of chances to criticize our system. We say, oh, India, blah, 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 that's not good, not good. But honestly speaking, we handle this pandemic way better the so-called powerful country of the world, which is US. Those people never follow any food regulations, any marks. I'm not complaining, I was telling that how kind of strong system we have. We need little bit modifications, and then we can do it, we can deliver it. When the so-called educated people in the Western world not following the simple rule of marks, they're holidaying in the beach. I have seen in the video in Andhra Pradesh a beggar wearing a mask. That's the beauty. That's the beauty. We responded to a crisis such a strong way, and that gives us a loss of confidence that we can do it if we work together. I can see that when I go to the highway, how we are giving way to this all these COVID ambulances. How we are working together in my community, but responding in a WhatsApp group. If someone is infected, we are bringing. There are many people infected in my third floor. I'm living in fourth floor, fifth floor. We are providing them household groceries on their doorstep. We responded in a community. This pandemic shows us that we can work together. Many things can be achieved. Okay, so that's the take-home message for you guys. Whatever topic we discuss is a teamwork. It's a proper blend of science and engineering. If you do together, if you understood fundamentally very strong, you're going to change the world. You guys don't confine and go to get a job after BTech and that's it. You see that you're going to produce job and going to innovation, they're going to change the world. So we have been thinking, can we do something? All of us thinking, yeah, if I could be a doctor, I could help someone. But you can also help. I'm thinking my perspective as a chemist, can you do something? So it is the chemist. They have been finding with the help of physicists, biologists, engineers, modern day challenges, hunger, poverty, pollutions, all those energy problems. So all of us, we can do out of the box, out of the self-chemistry, out of cell engineering that has been not considered so far, and we can develop something new tool that can be useful for the society. Okay, so with this is the picture of my laboratory. These are three my young students. They have decided to put their lives on stake on the young, mad assistant professor. We don't have much funding. I like to fun with them. They are enjoying. We have been working in a newly constructed laboratory with the worth of very interesting, research facilities there at SRMAP. And hopefully we can be able to produce some quality work. Let's see how it goes over the time. And with this, so some of the work that I have shown in the LED that I have done in the Los Alamos lab with my then supervisor Jennifer Hollingsworth. So she's a very renowned scientist, in this area. Of course, some of the latest work in the area you have been working. My PhD student Vasavi and Saida Kill, funding coming from SRM and Department of Science and Technology. I'd like to thank all of you. And this is one tagline I'm showing: if you like me, let's collaborate or die. This is the bottom line of, I have been seeing this tagline. I was attending MRS conference in Boston in 2014. There's a big scientist area putting this tagline. He almost like a Nobel laureate catcher, and that guy is looking for a collaboration. What he's going to gain it. So that's the nature of today's work. Don't confine yourself in silos, guys. This is again my last motivations. Just collaborate, or you're going to die. You're going to sign or pace. Choice is yours. It's a one-time chance in life. Do best. All the best. I'll be happy to have questions. Thank you so much.
Thank you, sir. Thank you, sir, for giving us such a nice presentation, particularly how the semiconductor nanocrystals can be put into light emitting application, and also how interdisciplinary research can benefit all of us. Thanks a lot. I'll request Chandan Ghosh, sir, if you have few words to say. So please continue.
Okay, thank you. Thank you. Thank you, Honorable Speaker, Dr. Monish Panda and Dr. Nimai Mishra, our Honorable Director, Dr. Piyush Pal Rai, our invited guests, students and fellow faculty. It's my privilege to have been asked to propose a vote of thanks on this enriching occasion. I, Chandan Kumar Ghosh, on behalf of R&D cell of Dr. Mishra Engineering College, extend a very hearty vote of thanks to our speakers, Dr. Panda and Dr. Mishra, for sharing with us your opinions and ideas on very emerging topic, the engineering of smart material, laboratory to industry. I also thank Professor Somadev Das, member R&D cell, for taking initiative in this organizing the webinar. Also thank to faculty coordinators, Dr. Nimai Chakraborty, Dr. Dola Sinha, Dr. Kamalika Tewari, for their active participation in this webinar. I would like to thank Mr. Abhijit Banerjee, member R&D cell, for his help in making the right arrangement of this webinar. This webinar will help a lot of students and fellow faculty members, researchers in the future with respect to their career and research. Thanks to all concerned to be present virtually in this webinar event during this pandemic scenario. We look forward to organizing more webinars for the interest of the students and faculty members for their technical enrichment. Lastly, I would like to wish everybody good health and safety. So thank you very much. Thank you all. And we are very happy to organize this type of webinar. And we hope that we will organize a series of webinar in the next time. And we will get the response from all corners as well. Thank you very much.
Thank you, sir. Yeah, thank you, sir. So can we disconnect now?
So we're leaving then, huh? Okay, thank you. Thank you for hosting.
Yeah. Thank you, Professor Mishra, for your enriching deliberation, and we are very happy to have you with us. So, yes, sir. And we hope that we will get you in future. Okay.
Sure. I'll have to visit. I'll have to visit whenever I go. I'll be in touch, and then love to visit more. Physical interactions will be much better with the students. Okay, sir. Okay, sir.
Okay. Thank you very much.
Okay. Thank you so much. Okay, then I'm leaving then. Okay.
Okay, one small announcement. All the registered participants will get the certificate from this webinar, and it will take a little time. I will take around 1 week time. After that, you will receive this through your email. Thank you.
Okay. All participants will get the certificate, or registered candidates will get the certificate?
Registered participants will only get. If anyone from the other
There are
than the
so many
registered ones, then I can arrange them.
You have registered but not yet participated.
Okay, so there is another.
Only participant will get the certificate. Is it?
Yes.
Okay. Okay, now this is the end of the event. Thank you very much. Thank you all for your cooperation, and hope you will be safe and secure in the pandemic scenario. Thank you all.